Okay, let's begin.
So, one case you guys were lucky, you escaped the quiz yesterday. On the other hand, it's been forever, so probably forgot a lot. Hopefully you start to review. I just remembered that our first test is actually next week, I think. So, what I'll do on our website, I'll post a review for the test as well as a mock test. So go through the review, study for what you'll expect it to be tested on, and then try the mock test and see how you do and sort of gauge from there. So at some point today or tomorrow, I'll have that posted for you guys. In the meantime, let's actually just continue. We're going to continue with approximate integration. So last time I derived the trapezoid rule for you guys. So next, I want to talk about the Simpsons Rule, because we already know about the midpoint left-hand and right-hand rule from Calc 1. So, something called Simpsons Rule. Okay. So, what we'll need here is how to find the area under a parabola. Given 3 points on the parabola. We're going to see how we apply this in order to approximate definite integrals. So at first, what we're going to do is we're going to center a parabola on the axes. So let's say that's your parabola. And here's a point. Here's another point. The goal is I want to find this area here. And given that I have these 3 points, right? Now, in general, this parabola can be anywhere in the xy plane, but I shifted around so that it's centered, so that the middle point I know falls right on the axis, and the other points fall here. So we can call this, say, x0. This would be x0 comma y0. This would be x1. This is x1 comma y1. And this is x2. And this is x2 comma y2. And we're going to call the distance between these guys here h, which is going to stand in for us to be delta x, but I'll write h because I don't want to write delta x all the time, as well as over here, the distance here is h. Right? How can you actually find that area? So suppose the parabola is ax squared plus bx plus c. From the picture, here are some things we can figure out from the diagram. One thing you can notice is that p of minus h is going to be, well, you're going to plug in h into x, minus h into x. You're going to get ah squared minus bh plus c, right? So that is just another way of actually writing y naught, by the way. You'll also notice that if I were to find p of positive h, in this coordinate here, that's going to be ah squared plus bh plus c. This is in fact another way to write y2. What you'll notice is that we can actually add these together. So I can figure out that y0 plus y2 is actually going to give me 2ah squared plus 2c. So we're going to come back to this. So remember that. I can add the y values at the end points, and I can get that expression, 2ah squared plus 2c. Also from the diagram, what you can notice is that, well, p of 0 is going to be c, right? So your c is basically going to be your y1. So we have these two equations. Right? So now let's find the area. Area under p of x on the interval minus h to h. How do we find that? Well, with an integral, of course. That's going to be the integral from minus h to h of a x squared plus bx plus c dx. The integral of that is going to be a x cubed over 3 plus bx squared over 2 plus cx between minus h and h. You evaluate this, you get ah cubed over 3 plus bh squared over 2 plus ch minus, now you take all the negatives, so this is going to be minus ah cubed over 3 minus bh squared over 2 minus, well, this is actually going to be a plus, minus ch. And if you combine these, what you would get is you would get 2ah cubes over 3. These guys will actually kill each other, and then I will get 2ch. So turns out this is an expression for that area. Let's clean this up a little bit. I'm going to factor out an h over 3. That's going to leave me with 2ah squared plus 6c. And then I want to now use these two equations that I derived down here. I can break this up into 2ah squared plus 2c plus 4c. This part here is going to be my y0 plus y2. And this part over here is going to be plus 4y1 by applying those equations. So this gives us h over 3 times y0 plus 4y1 plus y2. Okay. Or in other words, this is equivalent to me saying something like the following. If I think of my h as delta x, this means I have delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. Okay, so now let's generalize this. So here's how we're going to apply that to Simpsons rule. So that's the area under this parabola. I can think of it as delta x over 3 times that expression. Now Simpsons rule approximates the definite integral a to the b of f of x dx using parabolas. So remember, your left hand, right hand, and midpoint rule use rectangles. That's your typical Riemann sum. The trapezoid rule envisioned using trapezoids. But Simpsons rule actually uses parabolas. So if we have some function doing its thing on AB, what's going to happen is Simpsons rule is going to dissect this guy. It's going to create some points. And what it's going to do is it's going to approximate, it's going to go through these endpoints here, and it's going to find a parabola that moves through those 3 points. And then it finds another 3 points over here, and it finds a parabola that moves through those 3 points. And then it defines the area under the curve to be the area under these parabolas. And you'll notice here, the idea is this is going to fit closer to the curve because it's not like a straight line. It's actually curving kind of like how the curve itself is curving. So the idea is the errors between our approximation would be smaller. They'll actually catch up a lot faster with fewer subintervals. That's kind of the idea. Now, how do we apply that here? Well, if you notice, if I think of this area under this situation, let's say this is x0, that's x1, that's x2, that's x3, that's x4. And versus the area under, well, that's dead. Versus the area under here. What would the area over here look like? Well, we're going to take what we get from that. It's going to look like delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. And what would the area over here look like? Well, that's going to give us delta x over 3 times, now it's going to have f of x2 plus 4 f of x3 plus f of x4. And of course, the total area is going to be you adding these two guys together. Now what you're going to notice is that the last guy here and the first guy here are always going to coincide. So if you combine these, you're going to get 2 f of x2s. And if there was a third piece, the similar thing would happen. You'd have the first guy over here would be an f of x4, combined with that f of x4, you'll get 2 f of x4. And so if you put these all together, approximately equal to, you're going to get a pattern that looks like this. Delta x over 3 times, it's going to start off with f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3. You'll notice that you'll alternate 2's and 4's. It'll keep going dot 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 all the way until you get, say, your 2 f of xn minus 2 plus 4 f of xn minus 1 plus your f of xn. So you'll notice that the first guys and the first y value and the last y value, you don't do anything, but in the middle, you're going to alternate between 4's and 2's, starting with a 4, right? And that's this formula here. That's where that came from. Right? That's kind of how they figured it out. So, yeah, Trapezoid Rule, Simpsons Rule, these are the really new guys, and Trapezoid uses the area under trapezoids, which we know is 1/2 times the length of the two sides times the distance between them. You can use that to figure out this formula to approximate an integral, and using this parabola idea, where we actually we compute the integral and use it to help us approximate, we could find Simpsons Rule. One other thing that is peculiar with Simpsons Rule is that because to get a parabola you need 3 points, and you'll notice that under each parabola there are 2 distinct sections. So pretty much if you're going to apply Simpsons Rule, you would need an even number of subintervals. It won't work with an odd number of subintervals, because then if I had only an odd number, it means I would need 2 points to define a parabola, which isn't going to work. So that's one thing. It's not really a peculiarity in general, but it's a peculiarity when it comes to these formulas. Peculiarity of Simpsons Rule is that we must have an even number of subintervals. other than that, you kind of just follow a formula, kind of like you would know. But I thought it would just be nice for you to know where these formulas came from. So we would have covered, like I said, Formula 1, 4, and 5 in Calculus 1. Formulas 2 and 3, now you know where they came from. Now that you know where they came from, you just need to know how to use them. And in fact, whenever you have to use this on a test, I'll actually give you these formulas so you don't have to memorize them. I just wanted to show you where they came from. But I'll give you the formulas here on a test, like on a separate page or like at the back of the test. I'll also give you these formulas over here. So if you go to the second page, what you'll notice is that these guys here are the guys that describe the errors of these approximations. What is the error? The difference between the actual area under the curve versus the area that you get by computing this formula, that's called the error. And it turns out, for the midpoint, trapezoid, and Simpsons Rule approximations, we actually know how to find the error in terms of an upper bound. So let's talk about that, and then we'll jump into the examples. So, in our formulas, if you see R sub n, this means right-hand approximation with n right angles. Or let's say n subintervals. If you see L sub n, that means left-hand approximation with n subintervals. If you see M sub n, it means the midpoint approximation with n subintervals. If you see Tn, it means the trapezoid approximation. And if you see Sn, it means the Simpsons approximation. Now, E of, if I ask you E of Rn, this means the error associated with Rn, right? Etc. Right, you can't get it, I'm saying. We will cover the error associated with the midpoint rule, which now for shorthand we write E sub m, the error associated with the trapezoid rule, which for convenience I'll further abbreviate by that, and the error associated with Simpsons rule, which we will abbreviate by that. So now, E sub t, let's say, is defined to be the difference between the Tn approximation and the actual area under the curve. This is the error in finding the area using T sub n, right? Other E sub m, E sub s are defined similarly. So when you see these equations here, basically it tells us that we can find an upper bound for the error, meaning whenever we do these approximations, whenever we use these formulas on the reverse side of this page, I know how far away from the actual answer I can be. I can give you an upper bound on that. And I can say, I'm not more wrong than this expression, right? So whenever you need to approximate something, you need to guess an answer. The approximation isn't it's essentially worthless unless you can say how wrong you could actually be, right? You'll always want to know how wrong would the approximation be, and that's what these guys are for. So now, let's talk about one of these guys. Consider E sub n. Now these forms I'm not going to write because this is just outside of our scope. It can be shown that the size of our error, the magnitude by which we're off, give or take, plus or minus the area that we're going to be off, is going to be less than or equal to, right? So there's an upper bound, and it's given by this guy, k times b minus a cubed over 24n squared, right? Where n is the number of subintervals. AB is the interval under consideration. And your k is a constant such that in magnitude your second derivative is going to be smaller than or equal to k. So that's what you'll notice for these two here. For the e sub m and the e sub t, k is just some number that's always larger than your second derivative on the interval AB. Now, for Simpsons rule, you actually need up to 4 derivatives. Now, all of these error formulas actually have something different. Like I said, you don't have to memorize these. I'm going to give you these formulas. But you should also know that the k's in these formulas is also a number that you kind of have to figure out. It's just going to be pretty much the smallest number you can find on the interval, such that the second derivative is smaller than that in magnitude. Now, in terms of, what does it all mean, Basil? Like, I'd say it's just best to jump into the examples. So we're going to go through these examples. You will have questions like these on the test. I'm going to ask you to approximate the area under some curve, or ask you to approximate the value of some definite integral. I'm going to tell you how many subintervals you should use, and I can also tell you what rule I want you to use. So let's actually go into the examples on the handout. Let's do problem 1. And at this point, the midpoint rule is kind of boring. Let's just jump into B, the trapezoid approximation, since it's kind of different. Okay. Now, how would you actually find the error under trapezoid approximation for 0 to pi of the sine of x dx? Now, of course, I know you know how to find that by hand. You know how to find the exact area. But let's actually do an approximation on purpose. And I want to use 4 subintervals using n equals 4. So pretty much, I have my sine function, right? Of course it continues, but we don't care about that. From 0 to pi, and I want to approximate it using 4 trapezoids. Now those guys are gonna look like that, and like that, and like that. So I'm gonna find the area under these trapezoids as an approximation for the area under the sine function. Now in general, you don't need to sketch it, you just need to know that's what we're doing, right? So, how do you actually go about doing this? Well, the trapezoid approximation with 4 subintervals is going to be, well, delta x over 2 times f of the first y value plus 2 f of the second plus 2 f of the third plus 2 f of the fourth plus the final value. So you include all the endpoints, both the left and right extremes are accounted for, and all the y values in the interim are doubled, right? This was the trapezoid rule approximation. So pretty much what we're going to have in this case is we're going to figure out what is our delta x. Delta x is always going to be b minus a over n. That's a form that you learned in Calc 1. It is still true. So in this case, your delta x is going to be pi minus 0 over 4, or pi over 4. And this would mean that, to approximate that, it's going to be pi over 8 times f of x0. Well, our x0 is going to be 0. Our x1, let me actually show you how to find those intervals in case you forgot. So once you do that, what I like to do is I like to draw a picture once I find my delta x. And I just put in the values, 0 and pi. Then I do my dissections. And pretty much what I do is I put down the first delta x that I found here. And then you just keep adding it to find all the other ones. So you start at this, you add plus pi over 4. Then you add another pi over 4. Then you'd add another pi over 4. Then you'd add another pi over 4, and you should end at pi. Right? So if you take pi over 4 plus pi over 4, you get 2 pi over 4, which is pi over 2. 2 pi over 4 plus pi over 4, you get 3 pi over 4. 3 pi over 4 plus pi over 4, you get 4 pi over 4, so that's the endpoints. These guys are, this guy here is your x0, this here is your x1, this here is your x2, this here is your x3, this here is your x4, so in that formula. So you have one of these, this formula you'll have on the handout with you. So what you need to do first is find your delta x, then figure out what the subintervals are, what are the actual x values for the subintervals. Just draw a picture, mark off the subintervals, and then starting at the first endpoint, keep adding your delta x until you get everyone else. And now it's just a matter of plugging it in. So, the integral of sine x dx is going to be approximately equal to t sub 4, which we now know is equal to pi over 8 times sine of 0 plus sine of pi over 4 plus sine of pi over 2 plus sine of 3 pi over 4 plus sine of pi.
Isn't it 2 times?
Yeah, don't you put the numbers in front?
Yes, these should all be 2's. And other ones in the middle. Okay, now, I would expect you to know how to compute the trig function at the special angle. Sine of 0,
0.
sine of pi over 4, radical 2 over 2, so that's just radical 2. Sine of pi over 2,
1.
1, so that's just 2. Sine of 3 pi over 4. It's also radical 2 over 2 times the 2. Now you get the radical 2. Because 3 pi over 4 is in the second quadrant, the sign gives you the same value as in the first quadrant. Sine of pi, 0. So we end up with pi over 8 times 2 plus 2 rad 2. Could simplify it a little bit. So. Or pi over 4 times 1 plus rad 2. So that's not the exact area, that is just an approximation of the area. And that's how we can using probability. Yes?
Do we need to calculate the error for this or no?
In future examples. I'll ask you how to do that, but yeah, in problem 2, I asked you to find the error.
Oh, I didn't see that.
Yeah. So, but as for this process, do we know how to do it? Okay. So now, let me actually show you an example of finding the error. Right? So in problem 2, so of course I want you to do parts A and C on your own, and we'll probably rush through those next time, but just so you can know what to do here. So problem 2, part B, asks us for the error in computing T sub 4. So when you have to do that, what do you need to find? Well, I need to know what K is. That's going to be important. Okay. The other things we would have already have found from problem 1. So the B and the A we're going to know from the problem. So the A is actually the 0, and the B is actually the pi. So the thing that we're going to need is to know that what the K is. And we know K is an upper bound for the second derivative on the interval 0, pi. How do I find that? Well, I would first find the second derivative. So if my function is sine, my first derivative is going to be cosine of x. My second derivative is going to be minus sine of x. So this means we need K so that the absolute value of minus sine of x is less than or equal to K on this interval. Can you think of a nice number for which that is true? 1. Choose K equals 1, right? So you try to choose the smallest number that you can think of that's larger than that value. And then you're going to plug into the formula that you have here. So we know that the size of the error that I just computed with 4 subintervals, it is going to be less than or equal to K times B minus A over cubed over 12n squared. So the error is going to be smaller than K was 1 times pi minus 0 cubed over 12 times n is 4 squared. So it turns out pi cubed over 16 times 12. What is that roughly? Like as a decimal. Huh?
I just said it's small.
It's small. It's a small error, but just my calculator do that. Pi cubed divided by 12 times 16. So that's roughly 0.1615. So basically, what does that actually mean? It means this answer, it means what this means is that the answer pi over 4, 1 plus radical 2 is at most 0.1615 off the actual answer. That's what that actually means. If you were to compute the actual answer, which in this case we actually could, right? The integral of sine is going to be minus cosine between 0 and pi, and you're going to plug in pi, cosine of that is minus 1 plus 1. So the actual answer is 2. If you were to look at what this is, pi divided by 4. I'm just doing this for fun. Like you won't have to actually do it because you're not going to use a calculator anyway. Pi divided by 4 times 1 plus square root 2. This is 1.896. And we take the difference between those. So the actual error here is 0.104. So that's how much I'm off by, but it's smaller than 0.1615 is the idea. Right? So I know this number is going to be the maximum amount that I could be wrong by doing this. And for the trapezoid rule, for the particular function sine of x, in this case I was just off by 0.104. But the point of this guy is to just say, how bad could it be? How wrong could we be here in doing this approximation with the trapezoid rule and for subintegers? Yeah, that's kind of it. So what I want you guys to do is to go through the rest of these. We'll quickly go through them together, but I actually want you to try them because there are some situations where you can get confused. So do problem 1, parts A and C, complete problem 2, and then do problems 3 and 4. And in terms of what you could be tested on, I would ask you something like what I do here. So I'll give you an integral, I'll ask you to approximate it with something, and then I'll tell you what is the maximum error. Like I can ask all of that in one problem. It's also possible for me to ask you like a problem in 3, like a self-contained problem as well. So it just depends on the mood. So try those. We'll get through those next time. And next time we are going to start sequences in series once we get through all those problems. So, and your test will officially cover whatever I cover up to that point. So we're about a class or 2 behind, so we'll slow down a little bit to make sure you guys got it. But hopefully you guys have caught up to everything now and you're ready.
Okay.
It's in recitation next week, and I'll post, so it's next week Tuesday. The whole, you'll have the whole stuff.
An hour? An hour.
Yeah, 15 minutes to an hour.
An hour.
It'll be written so that you can, like I said, I'll post like a mock exam as well as a review, so you'll know what to expect.